Jupiter, more than just a distant swirl in our night sky, is a planetary anomaly, an enormous, churning world that seems alive in its complexity. From afar, it looks deceptively smooth, a giant orb wrapped in caramel bands. But once you get closer, everything changes. Beneath those stripes lies a vast, shifting atmosphere, alive with winds faster than any hurricane, storms the size of continents, and cloud systems that ripple and collide like fluid paintings in motion. It's not just the largest planet in our solar system, it's a physics experiment in progress. A planet so massive that its gravity warps the paths of comets. So large, it could hold more than 1,300 Earths inside. And yet, despite its scale, it spins faster than any other planet, completing one rotation in under 10 hours. But what really powers this giant? Why do its clouds never stop moving? What fuels the eternal dance of its atmosphere? Let's begin. Jupiter's atmosphere is made mostly of hydrogen and helium, the same elements found in stars. But unlike stars, Jupiter never ignited into nuclear fusion. It came close. If it had gained 80 times its current mass, it might have become a small star. Instead, it's a failed fire. A planet that glows with internal heat from its own formation, radiating more energy than it receives from the sun. That heat surges upward, pushing gas and vapor toward the surface, feeding motion in every direction. What we see on the outside, the pastel bands and swirling ovals, is only a small piece of what's happening inside. The surface we observe is a layered atmosphere, stacked in colors and zones. These alternating stripes aren't just random, they're powerful jet streams moving in opposite directions. Lighter bands are zones of rising gas, often containing ammonia ice clouds. Darker ones are belts, regions of sinking air revealing deeper, murkier layers. Each jet stream moves east or west, speeding at hundreds of miles per hour. At the equator, winds can reach over 400 miles per hour. There's no terrain to slow them down. Jupiter's atmosphere has no solid ground, no continents, no oceans, just depth. These jet streams form narrow, sharp boundaries that span the entire planet. But where they meet, turbulence. Massive shear forces tear at the clouds, forming wave-like patterns and wild storms. Among them, one stands apart. A swirling crimson oval carved into the planet's southern hemisphere, the Great Red Spot. It's not just a storm, it's a monument. A massive high-pressure system that's been raging for at least 350 years, possibly longer. It's shrinking now, but still, it could easily swallow Earth whole. This vortex spins counterclockwise. Its clouds spiral around a central eye, with winds reaching 268 miles per hour. The colors? Likely caused by chemical reactions high in the atmosphere, triggered by solar ultraviolet light acting on unknown compounds, perhaps sulfur, perhaps organic molecules pulled from below. Around it, smaller storms collide with its edge, sometimes merging, sometimes bouncing away. It influences weather across latitudes, disrupting nearby belts and spawning new turbulence in its wake. The red spot is a survivor. It's been absorbing smaller vortices for decades, growing denser, changing hue. In recent years, scientists have noted that it's not as red as it once was, more salmon pink, even orange.
Still massive.
Still powerful. Juno, the NASA spacecraft now orbiting Jupiter, revealed that the Great Red Spot reaches deeper into the atmosphere than expected, perhaps 200 miles down. It's a towering structure in a world of moving gas. But Jupiter doesn't rely on a single storm to show off. All across its face, storms erupt, twist, and vanish. White ovals spin in the cloud belts, anticyclones like the red spot, but smaller. Some form chains, curving across hemispheres like rows of pearls. In 2000, 3 of these white ovals merged to form one massive storm, eventually known as Oval BA. It turned red a few years later and was quickly dubbed Red Spot Jr. Beneath the belts, convection towers rise. Popcorn-like clouds bubble upward. Inside these, ammonia and water vapor meet conditions not unlike Earth's thunderheads. Only here, the scale is off the charts. Lightning crackles inside these clouds. Some bolts are thousands of times stronger than those on Earth. NASA's Juno spacecraft observed radio bursts, signs of massive discharges, echoing through the planet's magnetic field. But that's not the only surprise. Juno also discovered what scientists now call shallow lightning. This kind of lightning doesn't come from deep water clouds like we'd expect. Instead, it forms high up, within clouds made from a strange slurry of ammonia and water. Up here, where temperatures plunge to minus 126 degrees Fahrenheit, normal physics takes a detour. Ammonia acts as an antifreeze, melting ice into a mushy mix. These mush balls are hurled skyward, then fall back, smashing into each other and creating static charge. Lightning dances in the ammonia fog. It was this discovery that helped solve another mystery: Jupiter's missing ammonia. Early in Juno's mission, scientists noticed that ammonia seemed strangely absent in some parts of the atmosphere. Turns out, mush balls were dragging it deep down, locking it away beneath the clouds. And yet, even more lightning strikes rage deeper still, in thunderheads rising 30 to 40 miles tall. Here, water vapor exists in all three forms: solid, liquid, and gas. Just like Earth. But on Jupiter, the results are more extreme. Juno has recorded thousands of lightning flashes. Some last only milliseconds. Others pulse longer, leaving eerie afterglows across the dark planet. Now, let's pivot toward the poles. Here, the rules shift again. At Jupiter's North Pole, spacecraft revealed something truly strange: a perfect octagon of storms. 8 massive cyclones, each over 2,000 miles wide, circle a central vortex. They spin together in harmony, never merging, never drifting apart. Their shapes hold like gears in motion, balanced in place by invisible forces. Jupiter's rapid rotation and internal dynamics hold them in near geometric precision. The South Pole isn't far behind. Originally home to 5 surrounding cyclones, it eventually gained a 6th, forming a hexagon of its own. These structures remain stable, year after year. No model predicted this. The stability and symmetry defy expectations, forcing scientists to reimagine the physics of rotating fluids on gas giants. And above these poles? Auroras. But not like ours. Jupiter's auroras don't blink in and out. They burn constantly, lit by a magnetosphere 20 times stronger than Earth's. These shimmering rings of light, glowing in ultraviolet, are supercharged by the planet's rapid rotation and fed by volcanic material from the moon Io. Yes, a moon is helping fuel the auroras. Io's eruptions spew sulfur and oxygen into space, which gets swept into Jupiter's magnetic field. The rotating planet drags those particles toward its poles, where they crash into the atmosphere, igniting a show that never ends. Astronomers call them auroral footprints. Io, Europa, and Ganymede all create their own distinct bright spots within the auroras, physical evidence of invisible magnetic tethers connecting planet and moon. And when the solar wind arrives, the lights flare even brighter. Hubble has seen auroral curtains stretching thousands of miles above the planet. Some are visible in X-ray, some in infrared, none to the human eye. We've crossed the equator, dived into storms, peeked into polar cyclones, and watched lightning explode in ammonia clouds. Step away from Jupiter's storms for a moment, and you'll find something easily overlooked. Rings. Yes, Jupiter, the king of the planets, has rings too. But they're not the icy, radiant loops of Saturn. Jupiter's rings are subtle, wispy, thin. They're faint bands of dust that orbit just above the cloud tops, almost invisible unless seen from the right angle, with the right light. Discovered by Voyager 1 in 1979, these rings consist mostly of tiny particles, microscopic bits of rock, not ice, scattered and suspended in orbit. They don't reflect much sunlight, which makes them nearly impossible to detect from Earth. To spot them, you need infrared imaging or backlighting, when the sun's rays shine edge-on, catching the faintest glimmer of dust. And they're not random. They have structure. Jupiter's ring system is made up of 3 components. Closest to the planet is the halo ring, a wide, donut-shaped band of fine particles that spread out from the main ring. Then there's the main ring, a narrow, brighter strip of dust stretching directly around Jupiter's equator. Farther out is the Gossamer Ring, a faint, extended band made of overlapping material from tiny moons. But where does this dust come from? Not from Jupiter itself, but from its small inner moons, Métis, Adrastea, Amalthea, and Thebe. These moons are constantly pelted by meteoroids. When tiny space rocks slam into them, they kick up dust from the surface. Because these moons orbit close to Jupiter, the particles they shed don't fly off into space. They get trapped in orbit and slowly drift into the ring system. It's like an endless recycling loop. Impacts create dust. Dust becomes rings. Gravity keeps it all contained. Adrastea and Métis, the two closest moons, are the main sources of the main ring. Amalthea and Thebe contribute to the outer Gossamer rings. In photos captured by the Galileo and Juno spacecraft, these moons appear as tiny dots against the planet's vast disk, barely noticeable on their own, but critical to the ring system's existence. Even though these rings are faint, they reveal the same story Jupiter tells in every direction. Nothing is still. Everything moves. Everything connects. Now pull back even further. Jupiter isn't just a planet. It's a planetary system. Dozens of moons orbit this giant, from tiny captured asteroids to large, world-sized satellites. Each one is unique. Some are active, some are frozen. One in particular, Io, is unlike anything else in the solar system. Io is a volcanic inferno. Its surface is constantly reshaped by sulfur eruptions that shoot hundreds of miles into space. These volcanic blasts inject material into Jupiter's magnetosphere, feeding the radiation belts and influencing the planet's auroras. Then there's Europa, a frozen moon with a surface of cracked ice. Beneath that ice, a vast, subsurface ocean, possibly salty, possibly warm, possibly home to life. And Ganymede, the largest moon in the solar system, larger than Mercury. It has its own magnetic field, the only moon known to generate one. Its icy crust may hide a buried ocean as well. Even Callisto, the furthest of the Galilean moons, tells a story. Its ancient, cratered surface hasn't changed in billions of years. A frozen record of time. Each of these moons interacts with Jupiter, gravitationally, magnetically, and chemically. They tug on each other. They pull on Jupiter. They leave trails of influence that shape the planet's radiation, its atmosphere, and its magnetic behavior. Jupiter's magnetic field is another beast entirely. Generated by the motion of metallic hydrogen, a bizarre liquid form of hydrogen under extreme pressure, this field is enormous. It stretches millions of miles into space, far beyond the orbit of the moon. This magnetosphere traps charged particles, creating belts of radiation so intense they could fry electronics in moments. Jupiter's magnetosphere is the largest continuous structure in the solar system, even larger than the Sun's corona. It's so vast that if it were visible to the naked eye, a person standing on Earth would see Jupiter's magnetic bubble as bigger than the full moon in the sky. This invisible engine drives the planet's auroras, shapes its rings, and traps the plasma that streams from Io. It's not just a magnetic field, it's a force field. Everything on Jupiter, its clouds, storms, lightning, rings, and moons, exists under the influence of this vast magnetic structure. Let's tie it all together. Jupiter is more than gas and gravity. It's a machine, a heat engine, powered by the leftover energy of formation, still pumping out warmth from within. That heat drives convection. Convection drives storms. Storms drive lightning. And lightning shapes the chemistry of the atmosphere. Above that, winds race around the planet in alternating jets, dividing the atmosphere into bands. Those bands cradle and contain long-lasting vortices, the largest of which, the Great Red Spot, spins for centuries, a survivor in a world with no land to stop it. At the poles, storms arrange themselves with eerie precision, 8 around 1, or 6, depending on the hemisphere, locked in place like magnetic gears. Farther up, auroras blaze, fed by currents from the moons and particles from the sun. They shimmer in wavelengths we can't see. They hum in ultraviolet and X-ray. They pulse with Jupiter's 10-hour heartbeat. Even farther, invisible rings drift, faint remnants of dust, supplied by battered moons. And beyond that, more than 90 known moons orbit the gas giant, each one telling its own story. Everything in this system is connected, a constant exchange of energy, matter, and motion. We've been to Jupiter with spacecraft. Voyager gave us our first real look in the 1970s. Galileo went into orbit in the 90s. Cassini flew by. New Horizons 2. Now Juno is flying close, mapping its gravity, analyzing its fields, and peering beneath the clouds. And yet, for all that we know, Jupiter remains a puzzle. It is a planet that defies simplicity, a place where physics plays out on the grandest of scales. It is vast, it is violent, and it is beautiful. A place where storms can outlive civilizations, where lightning crackles through ammonia clouds, where rings whisper the stories of battered moons, where a magnetic field stretches beyond imagination, where auroras never end, and where, at its core, a churning ocean of metallic hydrogen spins endlessly, silently, driving it all. Thanks for watching. If Jupiter captured your curiosity, don't forget to subscribe, like, and drop a comment below. Let us know what fascinated you most. The Great Red Spot? The storm geometry at the poles? Or the invisible dust rings drifting in the dark? We're just beginning to understand Jupiter's role in shaping the solar system. And you're part of that journey with us. See you in the next deep dive.